Recommendations for electronic circuits prototyping. Use a 30-watt soldering iron to solder a component in Vero board. Use a soldering iron and sponge with water to clean the tip of the soldering iron. Use a good quality soldering wire to wire up your prototypes. Use a proper wire wrapping wire to wire up your prototypes. Use soldering fume extractor to protect yourself from the fumes of the soldering wire. Use a good quality tin-coated Vero board for your prototyping. Now we'll write a reset routine. We can write the reset routine anywhere between while loop, but I'll write the reset routine after counter routine, that is RSTR is the name of reset routine, and I'll add comments here, that is reset routine, and I'll write the reset routine before main program. Okay, I'll write RST_R and here we'll write the reset routine between these two braces. Here I'll read the status of switch 3 that is connected on port D6. So I'll copy the button function from the program. Here I'll copy this function, Control C, and I'll paste it here, Control V, and I'll change the port number, that is port D6. The bouncing interval is 50 milliseconds and active state is 0. So I'll change the comments here, port D6. Now I'll change this statement also, and here I'll reset the counter register and I'll write counter_reg equals to 0. Now here we will use another condition. If our counter will be in stop mode, it means that if SS flag will be 0, then we will be able to reset the counter. So we'll write here, that is if SSFLG equals 0, and here we'll close our first if condition. Here we can check if SS flag will be 0 and if our program will read the status of the switch which is connected on port D6 as 0, then it will move the value that is 0 to the counter REG. And now we'll write another subroutine to move the value of the counter to port B, where we have interfaced 8 LEDs with port B using ULN2803 Darlington driver. And here I'll write the routine to move the value of counter to the port B. And here I'll assign the name to the display routine, that is dispar. And I'll assign the comments, that is display routine, and I'll write the display routine before main program here, and I'll start writing display routine from here, that is disp_r. Here we will write the display routine and we'll move the value of counter REG to port B. So I'll go to the assignments, and from assignments I'll copy this assignment, that is LED PRT, Control C, and I'll paste it here, Control V, equals to, now I'll move the value of counter REG to port B. So I'll copy the variable from here, Control C, and I'll paste it here, Control V, and we have completed our program here. Now we'll compile the program and we'll check if there is any error in our program. Okay, now we'll compile it. Okay, our program is compiled successfully and there is no error in our program. But before downloading the hash file to the microcontroller, first we will check that how much delay will be produced by our delay routine. Here we have the delay routine, that is DLYR, and here we have used a variable, that is delay register, and we have assigned the value, that is 1000, to the delay register. Now we'll check that how much delay will be produced by our delay routine. For this we'll get the help from the debugging tool which is given in MikroC. Here we can see In Run menu, we have a Start Debugger option. We can press F9 or we can select this menu, that is Start Debugger. But before starting debugger, we will assign a toggle point at which our program will stop, and we would be able to see that how much time is left during the execution of subroutine. So here before delay routine, I'll place a breakpoint so that our program will stop before executing this delay routine, and we would be able to see that how much time is taken by the switch routine. For this, we'll go for Run menu and we'll select the option toggle breakpoint, or we can press F5 also. Okay, I'll select this option, and here we can see that we have a line which shows that here we have placed a breakpoint. Now we'll start the debugger. Okay, we'll go to the Run menu and I'll select the option Start Debugger, or I can press F9 function key. So I'll select this option Start Debugger, and here we can see that we have a red line which shows that here we have placed a breakpoint. But before debugging our program, here we will add some variables in variable watch window. Here we have watch clock window, and we can see that the time is 0 microsecond. Now we'll go to the select variable from list, and first we'll select counter reg. Okay, add. Now we'll go for SS flag. Okay, add. Here we have two variables, that is delay flag and delay register. So first I'll add delay register. Okay, add. And now I'll add delay flag. Okay, add. And here we have four variables, that is counter reg, SS flag, delay register and delay flag. Now I'll add both the ports, that is port D and port B in watch window, and from here I'll select port B, add, and I'll select port D now, port D. Okay, add. And here we have added two ports, that is port B and port D in our watch window. Now we'll debug our program, but before debugging our program, we will set the values at port D, because we have connected 4 switches on port D, from port D4 to port D7. As we can see from the schematic that we have connected 4 switches with microcontroller, that is at RD4, RD5, RD6 and RD7, and the logic of all these 4 switches is active low. We have connected the switches in a configuration that here we have a switch. One end of the switch is connected with ground, and second end is pulled up with 4.7K. and connected with a port, say RD4. This register is called pull-up register. And this switch is switch 1. If switch 1 is not pressed, the logic at RD4 will be high, and if we'll press the switch, then logic will go to low. And when we'll release switch 1, again the logic will go to high. That's why we call this logic active low, and we have connected all 4 switches on port D in same configuration. And we know that all these 4 pins belongs to the higher enable of port D. We can write the equivalent number that will be observed by port D by pressing or releasing any switch. RD0, RD1, RD2, RD3. Here we have the lower nibble of port D. Now we can write RD4, RD5, RD6 and RD7. Here we have the higher nibble of port D. We have connected all 4 switches on port D from RD4 to RD7, and here we have switch 1 and we have switch 4 on RD7. Now we can write the equivalent number if no switch is pressed, so all ports will be high. As we are not reading all these 4 pins from RD0 to RD3, so we'll assign the number 0 to all these ports. Now we can check the equivalent number in decimal is 240, and in hex we can write 0x F0H. If switch 1 will be pressed, the status of port RD4 will be 0 and the remaining ports will remain high, and we'll assign the number 0 to all these 4 pins, and the equivalent decimal number is 224, and in hex we can write 0x E0H. Now we'll assign these 2 numbers to debug our program. We'll assign these 2 numbers to the port D in MikroC to debug our program. If no switch is pressed, the number will be 240, and if I'll press switch 1, the number will be 224. Now here we can observe that the number at port D is 0. We'll assign the value 224 to port D. So here I'll write 224. It means that switch 1 is pressed. Now we'll run the debugger. We'll go to the run menu and we can select run pause option, or we can press F6. So I'll press the option run debugger, and here we can see the time lapsed is 50.26 millisecond, and the program is stopped after executing switch routine before delay routine, and the time lapsed is 50.26 millisecond. 50 millisecond is the debouncing time which we have assigned in button function. Here we can see that we have assigned the debouncing interval 50 millisecond. That's why we have the time that is 50 millisecond in watch clock. Here we can see that the switch connected on port D4 is low and the value is 224 at port D, and we can observe here in watch window that the SS flag, that is start stop flag, is 1 after execution of switch routine. Now we will release the switch 1 connected on port D4, and the value of port D4 will be 1, so the number on port D4 will be 240. It means that no switch is pressed, and here we can see that the time is 50.26 millisecond. Now I'll run the debugger again, and it will again stop at delay routine, and I'll press F6 again. Here we can see that the value of delay register is 1 now, and the SS flag is 1, and the time lapse is 50.34. It means that the time required to increment the delay register is 50.34 millisecond minus 50.26 millisecond, which was the previous time, equals to 80 microsecond, and here we can see that the value of delay register is 1. Now we'll press the function key F6 until the value of delay register will be 10, and we'll calculate the average time for one increment of delay register. F6, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here we can find the lapse time required to increment the delay register for 10. Now we'll calculate the difference. 51.10 millisecond minus 50.26 millisecond equals to 840 microseconds. This much time is required to increment the delay register up to 10. Now we'll divide this value, that is 840 microsecond, by 10, and we'll get the time for increment of 1 count in delay register. So here I'll divide this value by 10, divide by 10. Okay. Here we have the number, that is 84 microsecond. Now we know that the time required to increment the delay register by 1 is 84 microsecond. And here in our delay routine we have given the number that is 1000. The total time required to increment the delay register up to 1000 will be 84 microsecond multiplied by 1000. So I'll multiply this number by 1000 equals to 0.084 second, that is 84 millisecond. And if the value of delay register will be greater than 1000, the time lapse will be 84 millisecond, and after 0.084 second, that is 84 millisecond, the delay flag will be 1. And when the delay flag will be 1, so the counter register will be incremented by 1. In this case, the speed of increment of counter register will be very high. And if we would like to have the time that is 1 second, so we'll have to replace this value by a suitable number to get the time of 1 second. To get the delay time of 1 second, we'll divide the 1 second by 84 microsecond. So we'll get the number to get the time of 1 second, and we'll paste the number here. So here I'll divide 1 second time by 84 microsecond. So here we have got the number that is 11,904.7. So we'll replace the number 1000 by 11,905 and we'll get the time of 1 second. So I'll replace this number by 11,905 and I'll copy this number from here and I'll paste it here also. Control V. Now we'll compile our program once again and we'll observe the result. First we'll stop the debugger and we'll remove all breakpoints. And now we'll compile our program. Now I'll connect Picket3 programmer with prototype. And now I'll start Picket3 programmer software. And I'll go to the file, import hex, counter delay switches, right. Now I'll press switch 1. Here we can see the increment time for our counter is 1 second. Now I'll press switch 2, the counter is stopped, and I'll press switch 3, the counter is reset. Counter start, counter stop, and counter reset.